And now we're going to do force vectors. Force is a push or pull. A weight is a force, and vector, remember, is a magnitude with direction. So let's get into this. Vector quantities, again, have both a magnitude, which is a number, and a direction. It has to tell you which way it's moving. Force, moment, and velocity are all examples of vector quantities. When we are talking about vectors, they're giving a variable such as a or b. It usually includes an arrow, such as these, and I don't know that you can see that super well. So this just didn't translate well. Down at the bottom, this should be an arrow over the top. Illustrating vectors. Vectors are represented by an arrow showing the direction it's moving, the magnitude, so the size of the line matters, and then a sense, or which way it's going. The magnitude is the length of the line segment. It needs to be measured precisely and then scaled. Magnitude, in this case, is 3. It is 1, 2, 3 units long. Direction, 30 degrees counterclockwise from the positive x-axis. So think about math. X, y. This is moving counterclockwise 30 degrees from that positive x-axis. The sense is going to be indicated by the direction of the tip of the arrow. In this case, the sense is upward and to the right. So you look at this, which way is it moving? It's moving up and to the right. So if it's moving up and to the right, it's going to have a positive x and a positive y. That says it's going right and it's going up. That's your direction. So let's take a look. If it's going down and to the right, it's going to have a negative y saying it's going down and a positive x saying it's still going to the right. Negative y, negative x is going to be down and to the left, and then positive y, negative x is going to be up and to the left. You're also going to need some trigonometry when we're doing this. Don't let that word scare you if you haven't learned trigonometry yet. Some of you have done this in geometry. We tend to teach a lot of trigonometry in the geometry class. But we need to know some things about a right triangle. A right triangle is a triangle with a 90-degree angle in the corner. Remember, that's what that little square means. In every triangle, the sum of all the angles is 180 degrees. And good old Pythagorean theorem, if we know any two sides, we can find the other side by using a squared plus b squared equals c squared. Some of you may not have learned sine, cosine, and tangent. In sine, cosine, and tangent, we remember them by saying so, ka, toa. So, ka, toa. So if you ask me about sine, cosine, tangent, in my head I still say so, ka, toa, even though I learned this back in 9th grade. So the sine of theta, when we see that little 0 with a line through it, we call that theta, is going to be equal to the opposite, that's O and so, over the hypotenuse, which is h. Cosine of theta is going to be equal to the adjacent leg. So for this is our theta, then this is the adjacent, the one next to it, and this is the one opposite the angle, and this is our hypotenuse. So ka is going to be the cosine related to adjacent over the hypotenuse. Toa is going to be the tangent of theta is equal to the opposite leg over the adjacent leg. What does that look like? So this time we're using this triangle to represent forces. You're used to using these for just straight up like number measurements, like he went 10 feet this way and 5 feet this way. Now we're going to use those as forces, but it works the exact same way. So the adjacent side we're going to call Fx, that's the force acting on the x-axis. The opposite side we're going to call force y, the force acting on the y-axis. And then the overall force is going to be the hypotenuse, what this turns out to be. So that's just going to be F. So if we know that's just a different way to write all those. So that's going to be sine is so, opposite over hypotenuse. So opposite leg over hypotenuse. Ka, adjacent over hypotenuse. adjacent over hypotenuse, and this is theta, and tangent is going to be opposite over adjacent, or opposite over adjacent. If we solve for Fy in this one, we find out that the y component, the up and down motion of this force, is going to be the overall force times the sine of theta. That's actually just a function you plug into the calculator. And then the x is going to be the force times the cosine of theta. If they are negative, they are left. So if x is negative, that means that this direction is left. If y is negative, that means it is down. So, let's take a look at one. If the magnitude is 75 pounds and the direction is 35 degrees counterclockwise from the positive axis, and the sense is up and to the right, this is how we draw that vector. We draw this, it is 75 units long. Whatever our unit is, that's 75 of them. It is 35 degrees is this theta, we know the angle, and we have this sense that it's going up and to the right. So, solve for the force along the x-axis. That's force of A along the x-axis. We're going to use cosine of the adjacent leg over the hypotenuse. And this, just remember, means the leg that's next to the angle over the total force. A is being used as that total force. So we type in cosine 35 degrees into our calculator. We solve for f of vector A along the x-axis. So don't let this notation freak you out. This just means we're looking for the force of this vector that's moving this way. We just want to know how it's moving left or right. We plug those into our calculator, and we get 75 pounds times cosine 35, and we plug that in, we get 61.4 pounds. So if you're pushing this box, if you're pushing a box up this angle, you're pushing 61 pounds to the right. The rest of the weight you're pushing straight up. How much? Well, we're going to plug those in the same way. It's going to be 75 times the sine of 35, and it's going to be 43 pounds up. If we did it in the downward direction, and it would be clockwise from the positive axis, it's going to be down and to the right. It's going to be the same number, but it's going to be still moving to the right, so it's still positive. But if we do the y, we're going to find out that it is moving down 43 pounds. Okay, resultant force. Two people pulling on the same boat from shore. They're pulling with the same magnitude, which means they're equally strong. They're both pulling at 75 pounds of magnitude. What does that look like? So first we're going to put the forces on a diagram, and we're going to list them out. So label right and up forces as positive and left and down forces as negative. So we know that the force of A, person A, in the x direction is going to be positive. The force of person A in the y direction is going up, so that's going to be positive. Person B is still pulling to the right. Oh, those are both x's. They're both pulling to the right. Person A is pulling up, so they're going to be positive. Person B is pulling down. So if we break them down, that's what they look like together. So let's sum them up. So if we look at the sum of the two people pulling along the x-axis, so that's these two people pulling this way, then we can figure out that together they pull with 122.9 pounds. If we look at how it's going to move up and down, then if they're pulling at the same angle, the total magnitude, this one's going up, this one's going down, the boat doesn't move up or down, it just moves straight over to the side, and the total magnitude that they pull with is 122.9 pounds. The direction is 0 degrees from the positive axis, and the sense now is just to the right. So what does that mean? It means that these two are pulling together. They are pulling with 122 pounds to the right. This upward motion that person A is giving cancels out this downward motion. And so the resultant movement, the resultant force, is just 122.9 pounds to the right on the x-axis. Okay, now let's look at a resultant force of something that is not equal. So you have this hook, and it's holding two cables. One of them is hooked up at a 30-degree angle, and it has 400 pounds of force on it. The other one is hooked up at a 60-degree angle and has 300 pounds of force. Looking at this, first you try and get a sense of how it's going to move in what direction. And then you're going to figure out, do the math. So this one is pulling up and to the right. This one is pulling down and to the right. But because these forces are different, unless you are really good at your math sense, you may not have a good sense of which way this is overall going to move. So let's start with the first one. We know that it's 60 degrees and that it's pulling up. The hypotenuse is 300 pounds. So then we can find the force on the x and the force on the y. Do our sine, cosine. We find out that it's pulling 150 pounds along the x-axis and 259.8 pounds up on the y-axis for this cable C. Cable D, we're going to use cosine, and it's 346.4 pounds along the x-axis. It is 30 degrees down, so that's going to be negative 200 pounds in the y. To find out the overall movement, we're going to add them together. So 150 plus 346.4. And then we've got 259 minus 200. So if you put those on here, we can see how those forces work together. 259.8 pounds up, minus 200 pounds down, 346.4 to the right, and 150 to the right. We're going to add those together, and we're going to get a total force to the right of 396.4 pounds, and a total force up of 59.8 pounds. That is because the up component, the y going up, is 59.8 larger than the component going down. So the overall sense is that this is going to go up and to the right. So it's going to go over and up to the right, and if you were pulling on those two cables and you were pulling the object, it would end up starting here and ending here. It doesn't matter which way you put them, you're still going to end up at the same spot. So now if we work this backwards, if we know how far something is being pulled up, or what the force is pulling it up, and we know the force pulling it to the right, then we can find the resultant force using our a squared plus b squared equals c squared. So 59.8 squared plus 496.4 squared is going to give us the square of the resultant force. We're going to square them, square root the whole thing, and this overall is going to pull at 500 pounds of force. Magnitude 500 pounds. Now if we need to know this direction, then we can use this tangent formula. We know the opposite side